So I'm going to just try and start defining Hodge Theaters. So these constructions or collections of Fabrenioids are kind of this kind of anabelian whole where all the anabelian constructions that we need happen. It's not really important. So I'm going to give the definition, but you'll see that it's not so enlightening. And it might, the theory might eventually be simplified to the point where we can get rid of them. Anyway, without further ado, I'm just going to start constructing these things and talking about them. So in order to start talking about them, I need to talk about prime strips. So in order to talk about prime strips, we need to fix, x over f0. So where f0 is a number field, a punctured elliptic curve. Over a number field. Okay. And then we also need to fix k, an extension of f0. So this satisfies some hypothesis. I think we need to fix so this is a particular cusp. So this is a cusp. K, C, non-zero. And and then we need to fix a collection of valuations. So this is V, which in the paper is denoted by this. So this is the image of a section. So a set theoretic section of, there's a map from the valuations of, K to the valuations of F. Okay, and then we can take a section of this, F0, and the image of this is what we call this set here. So this thing here is S. So this is S of val F0. We can call this V. Okay, so this is sometimes called initial theta data. Okay, and I'll talk about this a little bit more. I have talked about this in other videos. Okay, so we need a definition, and these will. So let me just say what they are, and then I'll say something about them. So a prime strip of Fabrenioids, or I'll just call them prime strips, are tuples F, okay, where they're collections of Fabrenioids FV for V an element of V, where they satisfy certain things for different places. Where this Fabrenioid is, it's going to be a tempered Fabrenioid of this guy when V doesn't divide infinity and it's bad. So a bad non-Archimedean prime of our original elliptic curve. It's going to be one of these global Fabrenioids and then there's some particular cover here that I'm not going to describe, but these things are kind of simple. They're much easier to do than the non-Archimedean case. or sorry, in the bad non-Archimedean case. Okay, and then there's a crazy construction of a Frobeniaoid for odd holomorphic spaces. Okay, so when V divides infinity. So, okay, and then this is what a prime strip is. In a morphism of prime strips, is just a collection of morphisms. So let me say a little bit more about the notation of about some of this notation that I've been using. So notation. So, okay, if I take if I take z over k, and I write some subscript zv, okay, so this thing is just going to be z over spec k with kv. Okay, so this is going to be this variety here. All right. What else do I need to talk about? So this is gonna appear quite a bit. So in particular, this is the x double underline cover base change to this local field. So this is the completion of the field k with respect to the valuation v. Okay, so let me just make some remarks about this. So, well, okay, so let me just say that these global Frobeniaoids and these odd holomorphic spaces, these essentially encode monoids with actions, so various representations of the local Galois groups on various monoids, and that's why they're there. And so we're going to use them for some Kummer theoretic constructions. Okay. So again, this is okay. So let me give another definition. So a capsule of prime strips for a set T is I'm going to write it like this: Ft, where this is going to be a collection of FTs for T and T. Okay, so this is just a tuple of tuples. Okay, and a morphism of tuples, a morphism of capsules, is just a collection of morphisms. All right. Now we can define what a Hodge theater is, or I'm gonna just kind of write down what a Hodge theater is, and I'm gonna explain more of the important components later. So there's essentially four bridges, things called bridges in a Hodge theater. So let me just write these down now. So what I'm writing down is the big Hodge theater. Okay, so this is all the Hodge. Sometimes these little pieces are little fragments of this are called Hodge theaters. So in the center of the Hodge theater, there are two capsules of prime strips. So this is all local information along this line. So kind of adelic information. All right. Then there are four bridges, okay, that are in this Hodge theater. Okay, there's And then there's two sides of this Hodge theater, right? There's this additive or geometric side, and then there's the multiplicative / arithmetic side. And these correspond to again this division, this exact sequence for an arithmetic fundamental group into the arithmetic part and the geometric part of a fundamental group. Anyway, so what are these things? Well, these double arrows here represent polymorphisms or tuples of polymorphisms. Okay, and there's a bunch of there's four bridges. There's this additive evaluative bridge. There's a multiplicative evaluative bridge. There is a there's this there's kind of two synchronization bridges here. There's this additive one and a multiplicative one. Okay, and the synchronization bridges go from this local data here to global data. So down here we have a global Fabrenioid associated to this cover. Okay, and we have a global Fabrenioid here associated to this other cover here. Okay, and sometimes this is called D circle, and this is called D circle plus minus. So, and everywhere in Machizuki's notation, there's plus minuses everywhere. Okay. It also in his notation, I could write down what the names of each of these bridges are. So this is the theta bridge. Okay, this is the NF bridge down here. So there's some parts that I'm omitting that Machizuki includes, which are some dangly bits that correspond to arithmetic Fabrenioids here. Okay, so this is the theta plus minus bridge, is what he calls it, and then this is this theta L bridge. Okay. Anyway, I'm gonna not use that notation. All right. So what's up here? So up here, these are other prime strips. So more local information. So these are just the standard prime strips. All the prime strips are always the same, but this is a single prime strip as opposed to a capsule of prime strips. Okay, and here there's going to be some group actions acting on here, and then there's always actions of the. Okay, so let me just say what this thing is. So T here, this capsule, is isomorphic to this group, which is really. Or this set, I guess, which is really the cusps of this cover here, and this is isomorphic to this torsion group that we took a quotient by in the definition. And so these are isomorphic to this as this FL divide on times plus minus sets. Okay. Over here, on this side, J is the capsule. And then it's associated with this multiplicative symmetry. So this is where we're going to have we're going to quotient this thing by plus or minus 1. So this is equal to FL. So there's a fixed point in particular of this thing, which is 0. So there's a distinguished there's actually a distinguished guy in each of these guys. So which is the 0 element. Okay, and so this is isomorphic to the cusps of CK as so FL divide on times sets. So this is another group, this FL divide on times. Okay, so now we have these four bridges, and then in addition to this information, there's a relationship between the prime strips here and the prime strips here that are given by some sort of gluing relation, which we'll call this gluing. So there'll be an identification between here and here, using a subquotient, I guess. All right, so this is the big Hodge Theater. Now, it remains to describe what all of these things are and what these bridges are. So, I'm going to spend the rest of the time talking about these bridges. Alright, so I want to show you that it's possible to just write down all the bridges kind of succinctly. So I'm just going to do that, then I'm going to come back, and then you'll be able to see that you can just write down actually the definition of the bridges in one page. Okay, so I've managed to write down the definitions for the bridges, and here they are. So immediately you can see a couple things. So both the synchronization bridges, which are going from local data in the center to global data on the bottom, so these are global, are defined by taking a particular single morphism here, and then acting on it by, so a single polymorphism. So you can see the polymorphism is that you take a fixed morphism, and then we're going to compose it with two maps here, or sorry, two groups here. So we take a morphism, we act it on the left and right by particular groups, and then we take the whole set of those. So this thing accounts for indeterminacy, okay? But by choosing the groups that you act on the left and right, we're going to get a group action here. And then so what we'll do is we pick a particular point, we define the morphism for that point, and then this is an element of the capsule, right? And then to define the rest for the rest of the elements of the capsule, we just use this action to define it. So we extend it by the action. Yeah, so this is the synchronization bridge, so this is from the local and global. Same thing happens on the multiplicative side. So very similar. Unlike these synchronization bridges, the evaluation bridges are single polymorphisms for each for each capsule index and for each local index. Okay, so remember that prime strips are just collections of Frobinioids at each prime. And then we have we have a tuple of those, okay? So, and again, like I said before, this evaluation has to do with evaluation of the theta function at these torsion points, okay? And what we're trying to do is we're trying to extract Q parameters. Also, we have a single map here on the additive side, okay? All right, so I guess what remains to do is to explain exactly what each of these bridges is.